All right, so like I said, super short lesson. I think you'll find this to be fairly simple. We're going to be talking about three-dimensional figures. We're going to be talking about prisms and pyramids and cylinders and cones and spheres and just a whole lot of three-dimensional figures. So the first thing you should be aware of is one of the terms that comes along with that. Oh, we're not up there. A polyhedron, okay, is the first term that we're going to talk about. And I wouldn't say I use that term a whole lot, but in a question where it says a polyhedron has da-da-da-da-da, you should understand what they're talking about. So a polyhedron is a space figure, and a fancy way of, or a less fancy maybe way of saying that is a 3D figure, right? 3 dimensions. It has depth, it has width, it has height. So 3-dimensional figure whose surfaces are all polygons. Do you remember what a polygon is? We learned that in like chapter 1. A shape, but it's like a circle is not a polygon, right? It's a
shape with a side.
What?
Shape with side.
Yeah, it's got flat edges, right? So a square, a triangle, a hexagon, a pentagon, a rectangle, right? Those are polygons. They're closed figures that have flat edges to work with. So in a polyhedron, what you see there, anyone think they can name that for me, a more specific name for it?
3D rectangle.
A rectangular prism.
A rectangular prism. Okay, this is a rectangular prism. A lot of times with prisms like this, they will give you dotted lines. The dotted lines means they're the lines in the back. So I'm just going to draw these in. You don't necessarily have to draw these in, but I'm just going to show you how they'll represent it. So those dotted lines in back just mean they're there, but we don't see them right now, right? So this would be a polyhedron. In a polyhedron, there are going to be 3 different features that we focus on. One is this point right here. How many points like that do you see in this figure?
8.
There's 8. 1, 2, 3, 4, 5, 6, 7, 8. Any guess what we call that point?
Vertex.
A vertex. You guys are so smart. So that's a vertex, okay? There's going to be lots of, what's the plural for vertex?
Vertices.
Vertices. There are going to be a lot of vertices addressed in these figures, okay? So that's the first thing. The second thing is, we'll go here, an edge of the figure. An edge is just where 2 vertices meet, okay? So this is called an edge, and that is, you could say where 2 faces meet. I haven't told you what the faces are yet. Or where 2 vertices meet up. Okay, or connect, I guess, where 2 vertices connect. So that's an edge, okay? And then the last thing, let's see, we'll go purple. The last thing is called a face. Ooh, that was loud. So this is a face. A face is one of the polygons in the figure. Okay, so your face is always going to be a polygon. That could be a rectangle, that could be a triangle, that could be a square, it could be a hexagon. Okay, lots of different things that your faces could be. So we're going to be identifying some faces, some edges, some vertices in the different figures that we talk about, and then I'll get into our friend Euler. That looks like Euler, okay? Because he found something pretty cool that comes along with faces, edges, and vertices. So take a look at this figure. I'm going to just put a name next to this one. Not that I'm going to ask you to name these right now, but as we go, you're going to want to know what these figures are called. So Nico said this is a rectangular prism. Anyone think they know what this one would be called?
Triangular prism.
Yay.
What'd you say, Jared?
Pyramid.
Pyramid.
Wow.
A triangular You're right there. Pyramid. Okay. This is a triangular pyramid.
What's a triangular prism?
What is a triangular prism? Try to draw a triangular prism right now.
Did they just add the Euler to every word? Like rectangle Euler and triangle Euler?
What?
She's saying
Oh, Euler. Triangular. Oh, that's interesting. I don't think so. But that's funny. I've never.
It's not spelled like that.
It's spelled different. I've never thought about that before. That's funny. Triangular. Yeah. Did anyone try to draw a triangular prism?
No. Oh, and does it have the rectangle on the bottom?
It has a rectangle wrapping around it. So you could draw like a triangular prism would look like this.
Yeah.
Or it would look like,
How can you draw 3D shapes so well?
well, I have been drawing them for 17 years. And mine still look like this. So, some of you are going to draw these way better. Actually, all of you are going to draw them way better because you have notability. And notability is so nice with stuff like this. It's going to make it beautiful for you. Mine doesn't do the straight lines and all that. Okay, so triangular prism, triangular pyramid, rectangular prism. These are words we're going to use a lot in this chapter, okay? So take a look at this. How many vertices, edges, and faces does this figure have? So we would say this is a triangular pyramid. How many vertices does it have?
4.
It's got one up here, one here, one here, one here. So it's got 4 vertices, okay? How many edges does it have?
6.
1, 2, 3, 4, 5, 6. Okay. How many faces does it have?
4.
It's got a triangle on the bottom. It's got a triangle on the back. And then this is where it's kind of hard to show. It's got a triangle on the right side and a triangle on the left side, right? So there are 4 faces. Okay. The more you can visualize this like 3-dimensionally, the easier I think it becomes, right? So like this is a triangular pyramid, right? You got to try and see this in your brain. It's got a flat triangular bottom, right? And then triangle, triangle, triangle that wraps around. Okay. And if you're ever like, I've got a bunch of figures up here. If you're ever like, I need to see it, come grab one of my figures. Okay, so this takes us to Euler. Okay, Leonard Euler. That looks like Euler. Leonhard. I don't know. Leonard. It's Leonard. So he is Swiss. Maybe that's why. Maybe it's a Swiss version. And he found this relationship that links faces, edges, and vertices in a figure. Now, I'm going to give you 2 formulas, and I'm going to tell you right now that the only one I will ever test you on is the 3-dimensional figure, okay? So this one, I'm going to expect you to have memorized. It's the only formula, I think it's the only formula in this chapter that I expect you to just know. Which really, why? Maybe I'll give it to you. I don't know. Okay, so Euler's formula for a 3-dimensional figure is this. You take the faces plus the vertices, and it will always equal the edges plus something. Now take a look at the figure up above. If you take faces plus vertices, it would have to equal edges plus what?
Half. Well, no, minus half.
Negative.
No.
Never mind.
Someone said it's positive 2. Someone said negative 2. Edges plus 2, right? Faces plus vertices, so 8 equals the edges, 6 plus 2 would make it 8, right? So faces plus vertices will equal edges plus 2. I know what you were doing. Was that Josh? You were subtracting the 2 to make it, who said minus 2?
That's what
Oh, you said minus 2. You were subtracting the 2 to make it equal. Yes. All right, so faces plus vertices equals edges plus 2. That works in every single polyhedron. Okay, every three-dimensional object, that will work, which is so cool, right? That he could come up with that. The two-dimensional version, so if you take it and you make a net for the figure, right? So if this is, can anyone name this for me?
Hexagonal.
A hexagonal prism. Good. So in a hexagonal prism, if I were to make a net, remember nets from chapter 1? Okay, you're going to do some netting today. If I were to make a net for this, so lay it all out flat, there's a different formula because now the number of vertices that you have changed, right? Because right now this edge and this edge and this edge all share that vertex, but when we open it up, that vertex shows up in a few different places when you make it a net, right? So the formula for a two-dimensional figure, the net, right? This is the net version, is faces plus vertices equals edges plus 1. Okay. So 2 formulas. I need you to know this one. This is the one that I will ask you more about. Okay, so example 2 here. It says how many faces, edges, and vertices are in that figure, and then we use Euler's formula to verify it. Okay. There will come a time in your homework on a quiz where I'll say, you have this many faces and this many vertices. How many edges would that figure have? So you should be able to find it both ways. I'll show you that in a minute. But how many, let's start with faces. How many faces would you say this figure has?
7.
I know why you say 7. It's not 7.
6.
It's 6. Why do you say 7 and why do you now say 6?
Well, because I thought there was another like point thing on the back.
It's okay.
Oh, you were saying, well, that would be 8 then. If there was another point on the back, there would be
No,
2
not
more.
Just 1.
What?
This,
Yeah, I don't know. That would get you 8 if you did another point on the back. I think a lot of people see
Yeah,
this
that's
as a
odd.
face, and that's not a face. That's inside the figure. Okay, we're just talking about outside faces. So don't include that one. Faces wise, you have the back face. So 1 back here, 2, 3, 4 in the back, 5, 6, right? So 6 faces. How many edges?
no,
Yeah. 5. No.
I counted
8.
We don't. Yeah. Sorry, I counted.
6.
9. It's 6. It's
7.
It's just 6.
It's 9.
What?
It's 9.
Huh?
1, 2,
Oh, I
3,
faces.
4, 5, 6,
Oh.
7, 8, 9. There's 9 edges on that figure. Okay. How many vertices? 1, 2, 3, 4, 5. Okay, so then it says verify that you're correct with Euler's formula. Euler's formula says faces plus, oh my word, faces plus vertices should equal edges plus 2. So faces, 6, plus vertices, 5, should equal edges, 9, plus 2. Is that true?
Yes.
It checks out. Okay. Okay, so what if I said you have this setup? You have 10 faces, 12 vertices. How many edges do you have? What would you do?
10 plus 12 equals
Should be 20 edges.
10 plus 12 equals edges plus 2. Can I just tell you how many people do this problem wrong on the quiz?
I'd go wrong.
At least
Because people see this and they go the wrong way with the 2. If you're solving this, this is 22 equals e plus 2. and then they tell me that it's 24. Not because they don't know the math, just because they're rushing. So slow down, take away the 2, and there should be 20 edges if there are 12 vertices and 10 faces. Okay? Okay, last thing. Euler's formula for a 2D looks like this. So how many faces, edges, and vertices are there? Use that to verify that it works in Euler's formula. So now look at this. This is a net for what shape?
Square.
Cube.
A cube, okay? A net for a cube. So faces and vertices and edges, we need to know how many there are. How many faces are there?
6.
1, 2, 3, 4, 5, 6. Okay, so 6 faces. How many vertices?
8. 8.
12.
You have to count all of those.
There's 14, right? Every one of those points is a vertex. So you have 14 in the net. You wouldn't if it was folded up, right? How many would you have if it was all folded up?
8.
8, right? Okay, how many edges?
19.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, so verify it. Faces plus vertices should equal edges plus what? 1 this time. Plus 2 is the 3-dimensional. This is the 2-dimensional. So 20 equals 20, and it checks out. So you can say, yep, I'm pretty certain I have the right numbers here because it works in Euler's formula. Questions on that?